Hey Royals, in our last lesson we introduced the concept of adding and subtracting vectors. And we only actually worked with two vectors at a time. And the concept of vector components will make our lives a lot simpler when we have situations that have, say, a vector that acts east, and then one acts north, and then one acts kind of north or northwest, and we want to find out what the resulting vector is. And that resulting vector in this case would be rather difficult to determine, or it would require a lot of work because I would have to find out what the total displacement is, and then I would have to figure out the angle that this vector makes. Now, that is doable, but it's difficult. So the concept of vector components will make our lives a whole lot easier. And so we're just going to determine the pieces that every vector is made up of. And what I mean by that is consider the vector here on the top right of our page. And it's the blue one here. That is the vector A. So if I draw the vector A actually is made up of two pieces. It's made up of a horizontal piece. In this case, that's the east direction component. So I have an east portion of that vector and a north portion of that vector. And if I added the east vector and the north vector together, I would get the overall vector. What I mean by that is if I added the green vector and the red vector together, I would get the blue vector. Because if I walked along green and then I walked along red, I would get to the same location that blue ended up. Okay, so our job today is to discuss how do I determine the length of the horizontal piece and the vertical piece, or the east piece and the north piece. Okay, so this vector here makes an angle with the east direction. So I'm going to discuss everything in terms of that angle that it's making. Okay, so if I look at the cosine of this angle, and remember cosine, we had the acronym SOHCAHTOA. The cosine requires the adjacent and the hypotenuse. So my adjacent here is the east component, and the hypotenuse is the vector A, or the length of A. And if I rearrange this, or I multiply both sides of my equation by the magnitude A, I notice something interesting. I can find the magnitude of my horizontal component based off of just the magnitude of my vector multiplied by the cosine. Okay, I can also do something similarly and do it for the vertical component. And the vertical component, I'm going to use sine. So this was A north. And if I look at the sine of the angle theta, I require the opposite side's length, which is going to be the magnitude of our north, and I need the magnitude of the hypotenuse. So I'm going to take the opposite side, A north, and divide it by the magnitude of the hypotenuse, and I get a ratio for the sine of the angle theta. Now, similarly to what we did with the x component, if I multiply both sides by the magnitude of A, I find out that I can isolate for just the magnitude of theta n. Sorry, not theta n, a n. Okay? So the nice thing about doing this is that the horizontal piece and the vertical piece will always be 90 degrees to each other. So I can actually just use primary trig ratios to determine the resulting angle theta, or the result of adding my vectors together. Okay, so when would I ever need this? Well, there's a lot of times in our lives that we can break up motions of objects into a horizontal portion and a vertical portion. Take for consideration kicking a soccer ball. When the ball is kicked from my foot, it has a vector that is angled upwards, but that vector is constantly changing on me, and it has both a vertical part, how much it's going upwards, and a horizontal part, which is how much it's moving left to right. So I can break up and determine how much the ball is traveling left and right and up and down all at the same time. Okay, so consider this. In our last lesson, we had the idea that colinear vectors were easy to add. And that was the idea that if I had all of my vectors acting in the same direction, all north or all south, it was much easier to visualize and add them together. And we're going to use that same idea today in this lesson. So if I'm trying to add the vectors, and it's a bit difficult to see what I'm looking at right now, so I'll just kind of highlight the concept that I'm dealing with right now. So I'm trying to add the vector A, which is this one, plus vector B, which is this one, plus vector C. And you can see that the resultant vector that I get there is the addition of all of those. Now, what we want to do is I want to add the portions or the parts of each of these vectors together. So if I look at A, for example here, A I'm actually going to draw in red. Okay, so A has a X portion to it, which is this length here, which is in red, and it has a vertical portion to it, which is this one here, which I'm going to do in red. So that gives me the X portion and the Y portion of A, because that's the height of A, that's the height of my AY vector. Okay, and this is the length of A in the X direction, so I call it the AX vector. Okay, so if I look at B, B also has a length in the X direction. It goes from this location to this location. And so that will be my length of B in the X direction. It also has a vertical component, which goes from this height right here to this height right here. So that's the length of B in the vertical component. And then C moves from this location to this location. So I have a length in the X direction that goes from here to here, and so that's what we call CX. And it goes from this height at the very top to this height in the Y direction. So if I'm looking at the overall sum of these vectors, I'm going to say the length from the very beginning to the very end is the length of AX plus BX plus CX, all in the horizontal direction. And in the vertical direction, it would be the length of AY plus BY plus CY. So if I know how long each piece of my vectors are in the X direction, I can add those together. And I can add them to my Y direction lengths as well to get the overall length. Now I've noticed one thing in my note here. This SY should actually only go to that part there. So I'm going to just get rid of this piece right there. That's my SY, because it goes from the very beginning to the very end. So what I'm saying is I can actually take my vectors and I can relate them to X components and Y components, or the X parts and the Y parts. Okay, so let's do an example of this with actual numerical numbers so that you can see the beauty of components. Okay, so I want to add these two vectors together. I want to find the result of these two vectors if I add them together. Okay, so I'm going to start by drawing what I actually have here. So D1 I'm going to do in green. It's a vector that is acting in the east direction, right? So I can say delta D1 in the X direction, or east direction, I'll throw a little E there for east, is going to be 5.0 kilometers east. Now, what's its vertical part? It doesn't have one, so I'm not going to list one. But D2, if we look at D2, it's going to start from here. It's 8 kilometers long, and it's east 25 degrees north. So if this is east direction and this is the north direction, it's acting kind of like this. It's 8 kilometers long. So this is what I'm going to call D2. And it has a length of 8.0 kilometers. And my job is to determine the X component, the length of it in the X direction, which we'll call D2X, and the length of it in the y component, which I'll call d2y. Okay, so this angle inside is 25 degrees. Okay, so let's determine the x total for my sum of these two vectors. So the total sum of my vectors in the x direction will be the sum of the first vector in the, I keep saying x, it should be east and north. It's going to be the vector in the east direction. So I add the length of the blue one in the east direction plus the length of the red one in the east direction, because there's no other vectors that are going to act in that direction. And then I need the length of the vectors in the y direction. So the total displacement in the y direction is going to be the vector of d1 in the north direction plus the vector of d2 in the north direction. Okay, so let's start in on this. If I'm looking for the x component of them, the first one's easy. It's 5.0 kilometers east. Plus the second one, the x component of this, again, if I use the cosine, I'm going to get cosine 25 degrees is equal to d2 east divided by the hypotenuse, which is 8 kilometers. If I multiply both sides by 8 kilometers, I get 8 kilometers multiplied by cosine, let's fix that, cosine of 25 degrees. That gives me d2 east. Okay, and that's just the magnitude of it. Okay, so that tells me that in the east direction, I have 8.0, I guess it should be 0.0, kilometers cosine of 25 degrees. And I need to, and that's going to be acting east. And I'm going to add these together. So I need to determine what 8 cosine 25 is and add it to 5. And if I go ahead and do that, I get 10.25 kilometers east. And let's go ahead and deal with the y components. The y components is really easy because the first one here, delta dy, there is no y component for the first vector. It's 0. So I need to just add it to the y component of the red vector. So if I add it to the y component or the north component of the red vector, I can find out that it's 8.0 kilometers. And I'm going to use sine of 25. And that's from the fact that our y component or the north component is the sine of the angle. Okay, so here we go, delta dy, and I get that the y component, if I work this calculation out, I get 3.38 kilometers. So now I actually determined the resultant east direction vector to be 10.25. So that's this. So delta d in the east direction is 10.25 kilometers. And I know the change in the y direction is actually 3.38 kilometers, and that's my delta dy, or sorry, north. I keep calling it y, it should be north. Okay. And here we go. So my resultant would be from the very beginning to the very end. So we need to determine the magnitude of delta d. Okay, so the magnitude of delta d, Pythagorean theorem comes back to save us again. So delta d east squared plus delta D north squared. And I get 10.25 kilometers. And I'm going to square that plus 3.38 kilometers. And I'm going to square that as well. Delta D. I'm going to square it. If I work this math out, I get a value of 116.4869 kilometers squared, which is my square of the displacement. I don't want that. I want the actual displacement vector magnitude, and that gives me 10.79 because I took the square root of that vector. Now, I need to determine the angle, theta. So again, just like we did before, I'm going to use the trigonometric ratios, and in this case I'm using tan. So tan theta, because I have the opposite side and the adjacent side, will become delta D in the north direction, magnitude, divided by delta D in the east direction, magnitude, which means that I have tan theta of 3.38 kilometers divided by 10.25 kilometers. And if you work through the math on that, you get an angle of 18 degrees. So overall, what's my overall displacement? Therefore, delta D is going to be 10.8 kilometers east, 18 degrees north. Okay, so that gives you an understanding of what components are, and we will work on a couple more of these in class when we get together again.